Here we're going to do a nice classic find the sum of an infinite series video. So the series we're going to look at is the sum as n goes from 1 to infinity of 1 over n times the quantity 4n squared minus 1. So I'll let you guys check this on your own, but this thing will converge by the limit comparison test. You can compare it to 1 over n cubed, and 1 over n cubed converges by the p-series test. Or you could probably show that this converges with maybe the integral test as well. That wouldn't be too bad. So let's go ahead and decompose this in a way so that we can find the sum the first way. And here we're going to use partial fractions, being motivated by the fact that we have a rational function as our summand. So, like I just said, our goal is to write this 1 over n times 4n squared minus 1 as a sum of, in this case, 3 different terms because we've got a cubic in the bottom. Now, I first want to notice that this 4n squared minus 1 factors to 2n minus 1, 2n plus 1. And so that's going to really aid us in our decomposition. So that tells us that we should be able to write this out as a over n plus b over 2n minus 1 plus c over 2n plus 1, where we need to find out what a, b, and c are. All right, so taking the standard strategy of partial fraction decomposition, we'll take this whole equation and multiply by the n, 2n minus 1, 2n plus 1, in order to make it a little easier to deal with. So notice that's going to multiply the left-hand side and just give us 1. And then on the right-hand side, we'll have a times, well, the n cancels, and we're left with 2n minus 1 times 2n plus 1. But I'm going to go ahead and rewrite that as 4n squared minus 1. Now next, we're going to have a b. But now the 2n minus 1 cancels with this 2n minus 1, and we're left with n times 2n plus 1. But I'll go ahead and write that as 2n squared plus n. And then we have a similar thing happening with the c term. The 2n plus 1 will cancel, and we're left with 2n squared minus n. Great. Now this may look like a single equation, but this equation has to be true for all values of n. So that actually gives us a system of 3 equations. One from the constant terms, which I'll just write like with a 1. One with the coefficients of n, and then one with the coefficients of n squared. So let's see what we get for each of those parts. So the constant term on the right-hand side will be negative a from this a times negative 1, and that's it. All the rest of them have an n in there. And then on the left-hand side, we have equals 1, because that's the only constant term. Well, that's the only term on the left-hand side. Now let's see what we get for the coefficients of n. So on the right-hand side, there's nothing from this first bit. Then here we have b minus c. So b minus c, and so that's going to give us b minus c equals 0 because there's no n over here on the left. Then finally the n squared term, so that's going to give us 4a plus 2b plus 2c. Here we have a times this 4n squared, b times that 2n squared, and that c times that 2n squared. And then again, we're going to have a 0 over here on the left-hand side because there's no n squared over here. Good. Now, notice we immediately see that this tells us that a equals negative 1, so that's good. And then this tells us that b equals c. But now, if b is equal to c, we can go ahead and plug that in here along with the a equals negative 1. And we see that this is going to collapse to minus 4, because we have 4 times negative 1, plus 4b equals 0. Again, because b equals c. But that is going to tell us that b and c are both equal to 1. Because here we can just add the 4 over and divide by 4. We get b equals 1, but then b and c are the same, so that means c is also 1. Okay, good. So that tells us that we can take this thing and we can rewrite it in this form with these values of a, b, and c that we have just calculated. So let's go ahead and do that. So I'm going to write this as the sum, n equals 1 to infinity of, I'm going to write this in a slightly different order. I'll write this as 1 over 2n minus 1 minus 1 over n plus 1 over 2n plus 1. Great. Now what I want to do is maybe clean this up so that we can look at this a little bit more carefully. So now I'm going to do something that's a bit trivial, like it's an easy calculation, but it's extremely helpful. And the motivation is we want to symmetrize this a little bit. So notice we've got this 1 over 2n minus 1, this 1 over 2n plus 1. Those are both 1 over odd numbers. But then this 1 over n is really 1 over anything. But if we use this very simple fact that 1 over n is the same thing as 2 over 2n, which is the same thing as 1 over 2n plus 1 over 2n, we can rewrite this in a kind of more symmetric form. So let's go ahead and do that. So just to reiterate, I am replacing this 1 over n with this sum 1 over 2n plus 1 over 2n. So that is going to give me the sum, as n goes from 1 to infinity, of 1 over 2n minus 1 minus 1 over 2n. So that's like the first term. And then to keep it like looking kind of symmetric, I'm going to write this as 1 over 2n plus 1 minus 1 over 2n. So I've just rearranged what's being summed here. Great. Now, the next thing that you can do is check that each of these series will converge on their own. And we'll actually see that by the way we calculate this, but that means you can split this up into two sums. So that's exactly what we're going to do. So let's split this up into the sum as n goes from 1 to infinity of 1 over 2n minus 1 minus 1 over 2n plus the sum as n goes from 1 to infinity of 1 over 2n plus 1 minus 1 over 2n. Great. Now what I want to do is notice what each of these are. So I'll write out a couple of terms for each of these, and that'll give you a feel for exactly what these series are. So notice the first term here is going to be 1 over 1 minus 1 over 2. So that's the n equals 1 term. The next one is plus 1 over 3 minus 1 over 4 plus 1 over 5 minus 1 over 6, and so on and so forth. So the awesome thing is that that is the alternating harmonic series. Now let's see what we've got going on over here. So I'm going to maybe write this as, so our first term is minus half plus third. So I changed the order a little bit there, but that's okay. And then the next one is going to be minus fourth plus 1/5. So notice we're missing that 1 over 1 term because this starts with 1 over 2n plus 1 instead of 1 over 2n minus 1. And then it keeps going. So our next one is minus 1/6, minus 1/6 plus 1/7, and so on and so forth. So notice that this is also the alternating harmonic series, almost. If we go ahead and add 1 to this and subtract 1 on the outside, now we have this guy and this guy are exactly the same. Now I'm going to go ahead and bring that minus 1 out front, and then I'll combine these things together into twice the sum of the alternating harmonic series, and I'll write that as the sum n equals 0 to infinity of minus 1 to the n over n plus 1. So let's just check that that makes sense. If we plug in n equals 0, we get 1 over 1, good. N equals 2, negative 1 over 2, and so on and so forth. So this checks out. Okay, so we're running out of room. I'll bring this up and then we'll finish it off. So on the last board, we got our goal sum down to this point where we have negative 1 plus twice the alternating harmonic series. Now I'm going to take this alternating harmonic series and rewrite it as a power series which has been evaluated at a certain point. And so in other words, I'm going to write this as minus 1 plus twice. Now we have this sum n equals 0 to infinity minus 1 to the n times x to the n plus 1 over n plus 1. I want to evaluate that at x equals 1, evaluate it at x equals 0, and subtract. So notice evaluating at x equals 1 regains the alternating harmonic series. Evaluating at x equals 0 just kills everything off, so we don't have that anymore. But the advantage here is that all of this stuff that I'm putting in green looks like a definite integral. So it looks like the integral from 0 to 1 of x to the n dx. And that's exactly what it is. So we're going to replace that with that integral. So now we have minus 1 plus 2, this sum n equals 0 to infinity, minus 1 to the n, and then the integral from 0 to 1 of x to the n dx. Now we're going to change the order of summation and integration, which we're allowed to do. I promise I'm going to do a video on exactly when you can do that in the future, but I haven't quite gotten to it. So let's do that and see what we get. We have minus 1 plus 2, and now the integral from 0 to 1 of the sum n equals 0 to infinity minus x to the n dx. So I've gone ahead and combined that minus 1 to the n and the x to the n. But now this looks like a geometric series with first term 1 and common ratio minus x. So we know geometric series add up to a over 1 minus r, and so that means we know exactly how this adds up. This is minus 1 plus 2. Now we have the integral from 0 to 1 of 1 over 1 plus x dx. So it's the starting term over 1 minus the common ratio. The common ratio here is minus x. But now that's a pretty simple calculus 1 type integral. That gives us minus 1 plus twice the natural log of 1 plus x. We need to evaluate that from 0 to 1. So evaluating at 1, we get log 2. Evaluating at 0, we get log 1, which is 0. So in the end, we have our final answer, minus 1 plus 2 natural log of 2. So we found the value for our goal sum. So now I'm going to go ahead and clean this up, and we're going to look at another solution. Now we're going to look at a second way to calculate this sum. So before, we did something that looked like a partial fraction decomposition that ended in a little bit of integration. Here we're going to start with integration, and in fact we will move through a triple integral. So the first thing that I want to do is what we did kind of first last time, which is factor this denominator. So let's go ahead and do that. So we've got this sum as n goes from 1 to infinity of 1 over n times 2n minus 1 times 2n plus 1. Good. Now the next thing that I want to do is notice the following formula, which is pretty easy from calculus 1, and that is if you take the integral from 0 to 1 of u to the m du, you're going to get u to the m plus 1 over m plus 1. We need to evaluate that from u equals 0 to 1, so you get 1 over m plus 1. So in other words, a strategy for getting these kind of terms could be looking at this type of integral. And so we're going to, in fact, replace 1 over n, 1 over 2n minus 1, and 1 over 2n plus 1 with an integral like that. And we'll use a different variable for each. So let's go ahead and do that. So we're going to have the sum as n goes from 1 to infinity, the integral from 0 to 1 of x to the n minus 1 dx. So that's going to take care of our 1 over n thing. And then the integral from 0 to 1 of y to the 2n minus 2 dy. So that's going to take care of our 1 over 2n minus 1 thing. And then finally, the integral from 0 to 1 of z to the 2n dz. Great. Now the next thing that I want to do is do a little bit of a change of index here. In other words, we're going to re-index the sum. And that's just to make this look a little bit more familiar. So I'm going to replace n with n plus 1. And so that is going to make this sum start at 0 instead of at 1. And that's also going to change this, so it's x to the n, this so that it's y to the 2n, and this will be z to the 2n plus 2. So this isn't strictly necessary, but it just makes things look a little bit more familiar. Great. Next, I'm going to combine that product of 3 integrals into a triple integral. So let's see what we get when we do that. So we've got this sum as n goes from 0 to infinity of integral 0 to 1, integral 0, 1, integral 0, 1 of x to the n, y to the 2n, z to the 2n plus 2. And now we have dx, dy, dz. Next, I'm going to move my sum inside of the integral, and then we can rewrite that stuff that's inside as some big term that's being raised to the nth power. Notice here we've got x to the n, y to the 2n, which is like y squared to the n, and z to the 2n plus 2, which is like z squared to the n times an extra z squared. So let's kind of do that all at once. So we've got, this is going to be equal to, so we've got this triple integral 0, 1, 0, 1, 0, 1. And now on the inside, we have the sum n goes from 0 to infinity of, let's go ahead and take this z squared out front. And then we have x, y squared, z squared, all of that to the nth power. Good. And then here we have dx, dy, dz. Now we can use the fact that this is like a geometric series right here, where your starting term is the number 1 and your common ratio is x, y squared, z squared. So we know that that sums to the starting term over 1 minus the common ratio, the standard formula for a geometric series. So we can write this as integral 0, 1, 0, 1, 0, 1. Then we're going to have z squared over 1 minus x, y squared, z squared, dx, dy, dz. So we end up with something like that. Okay, good. So now I'm going to go ahead and transpose that up here, and we'll move on to the next step. So previously we've written our goal sum as this triple integral using tricks involving geometric series and stuff like that. Now we're going to start evaluating this integral, starting with the inside integral, which is with respect to x. So we've got a choice what order we do this integration in, and we're going to do the x integral first because this integrand is simplest with respect to x. So notice we can write this as now a double integral, 0, 1, 0, 1 of minus 1 over y squared, and now we have the natural log of 1 minus x, y squared, z squared, where we are evaluating x from 0 to 1, and then dy, dz. So let's talk our way through that. So if we take the derivative of that log term with respect to x, that's going to send the argument to the denominator, which is what we have. But then by the chain rule, we'll also have to multiply by negative y squared times z squared. So the minus sign will cancel that minus sign, the y squared will cancel that y squared, and then we'll get a z squared. So this checks out. This is the appropriate antiderivative. Now if we plug in x equals 0, we get natural log of 1, which is 0. If we plug in x equals 1, that just replaces all the x's with 1s and gives us our double integral. So this will be the double integral 0, 1, 0, 1 minus 1 over y squared, and now we have the natural log of 1 minus y squared, z squared, dy, dz. And now it's not super obvious what order we should do the last two integrals in, but I checked both ways and I think this is a little simpler, this dy dz order. So I'm going to use the fact that this argument of the natural log is a difference of squares, so I can factor it like 1 minus yz times 1 plus yz. And then on top of that, I can use logarithm rules to split that up. So I can split this up into, I've still got this double integral on the outside, 0, 1, 0, 1. And then I have 1 over y squared, that is negative times the natural log of 1 plus yz minus 1 over y squared, natural log of 1 minus yz. Good, and then I'm doing dy, dz in that order. Okay, so now I'm not going to do all of the details. I will sketch out the details, but I do want to notice that we have to take this antiderivative here, eventually plug in y equals 0 and y equals 1, or maybe take a limit, and that antiderivative is going to involve doing integration by parts. So let's go ahead and write that down. So our intermediate goal at this point will be the antiderivative of the following. So it's going to be the antiderivative of minus 1 by y squared, natural log of 1 plus yz with respect to y. So since this is an inverse function, well, natural log is an inverse function, and we're doing an integral, well, the hint here is you should probably use integration by parts. So we'll let u equal that inverse function, natural log of 1 plus yz, and then we'll let dv v be the rest. So that's going to be minus 1 by y squared times dy. Now we can populate the rest. So du will be equal to, so notice this is going to be with respect to y, so we'll get z over 1 plus yz. Again, using the chain rule. And here, taking the antiderivative, we will get v equals, so that's going to be 1 over y. Great. Now we use the standard integration by parts formula that says that we do u times v minus v du. So let's see what that's going to give us. That's going to give us 1 over y times natural log of 1 plus yz. And then v du, so that's going to be minus the integral of z over y times 1 plus yz, and then dy. Good. But what I want to notice here is that this is set up to do some sort of partial fraction decomposition. So hopefully we can write this as a over y plus b over 1 plus yz. Again, y is our variable here, z is a constant in this setup. So let's see if we can do that. We'll take this whole equation and multiply it by the denominator, and that's going to give us a new equation that does not involve any fractions. On one side of that new equation, we'll get z, and that's from multiplying this by y times 1 plus yz. Then on the other side, we'll have a times 1 plus yz. Now we can extract this into two equations, one having to do with the constant term on both sides of the equation, and the other having to do with the coefficient of y on both sides of the equation. So the constant term on the right-hand side of the equation is just a, and then on the left-hand side of the equation is z, because again, remember, y is our variable and z is our constant here. And then the coefficient of y on both sides, well, over here we have az plus b equals 0. So notice we already have a equals z, and then notice b is going to be minus a times z, but that means b is going to be minus z squared. So we've got a value of a and a value of b. So that means we can rewrite this as, well, we can just bring this 1 over y down, natural log of 1 plus yz, minus, now this is going to be the integral of, so we've got a over y, but that's going to be z over y minus z squared over 1 plus yz. And then this is going to be dy. Good. So now I'll go ahead and point out that we can take the antiderivative of that. It's not too bad. We'll have z times the natural log of y for this first term. And then we'll have minus z times the natural log of 1 plus yz for that second term. Notice the z squared became just a z because of the chain rule. It gobbled up one of the powers of z. So in the end, our antiderivative for this thing is going to be this guy right here minus all of this. So that's obviously going to change the sign there. Okay, so now that we're all set with that, the other one will go very, very similarly. So I'll maybe let you guys check that, and I'll jump right from this point right here to the single integral that you get from evaluating all of those parts. Okay, so we've skipped some steps, but we outlined our good strategy for getting to this point. So we've reduced this double integral down to the following single integral with respect to z. So we've got integral from 0 to 1, z times natural log of 1 plus z minus z times natural log of 1 minus z, plus natural log of 1 plus z plus natural log of 1 minus z. So I'm going to do one of these carefully and then leave the rest of them for you guys to check. As you can see, this is a really long process, and I think this would be maybe too long of a video if we did every single detail. So I'm going to do this one that I underline here. So, and I'll just calculate the antiderivative. So we want to calculate the antiderivative of z, natural log of 1 plus z dz. So again, this involves an inverse function, which means we need to use integration by parts. We'll go ahead and let u equal that inverse function, natural log of 1 plus z. That's going to make dv the rest, which in this case is z dz. So from here we can calculate du, which is 1 over 1 plus z times dz, and then v, which will be half z squared. Great. Now we can use our standard integration by parts formula to write that as u times v. So we've got half z squared times natural log of 1 plus z minus integral v du. So that's going to be minus, I'll bring this half out front, and then the integral of z squared over 1 plus z dz. Great. Now, here we've got a rational function, and we probably want to simplify a little bit before we can move on. And unfortunately, or fortunately, it's just the fact that we have to use some sort of division of polynomials in order to do that. So maybe we'll fit that in right here. We want to divide 1 plus z into z squared. So the first part of our quotient will be z. That'll give me a z squared plus z here. I need to subtract all of that. That gives me a minus z. So the next part of my quotient will be a minus 1. That gives me minus z minus 1. Subtract all of that. That gives me a 1. So my remainder is 1. So that tells me that I can take this thing that I'm circling in green and rewrite it as quotient plus remainder over divisor. In other words, z minus 1 plus 1 over z plus 1, or 1 plus z. Good. So together with this thing out front, let's see what we've got. So we've got 1/2 z squared, natural log of 1 plus z. So that comes from our first bit, minus 1/2 the antiderivative of z minus 1 plus 1 over 1 plus z dz. And now that last antiderivative is not so bad. So let's see. This is just going to come down, half z squared natural log of 1 plus z, and then we're going to have minus quarter z squared. Again, like from the half times half, and then plus 1/2 z, and then minus 1/2 natural log of 1 plus z. So those are all of our parts right there. Okay, and then a similar strategy can be employed on this other one. So I'll skip that on this other. So a similar strategy can be employed on this, and then these remaining two are not so bad. So I'm going to jump to the point where we have this full antiderivative. So in the last board, we sketched out how to take the antiderivative of this thing that's underlined, and now using a similar strategy, we can find the antiderivative of this, and then these last two terms are actually quite a bit simpler. So that ends with the total antiderivative of everything being minus z plus half 1 plus z squared times the quantity natural log of 1 plus z minus natural log of 1 minus z, and then plus z times the quantity natural log of 1 plus z plus natural log of 1 minus z. Now we need to evaluate that from z equals 0 to 1. So the first thing that I want to notice is if I plug z equals 0 into this, everything cancels. So obviously plugging z equal to 0 here cancels it. Then we have natural log of 1, natural log of 1, natural log of 1, natural log of 1. So those all cancel. So now all we have to worry about is plugging in z equals 1, keeping in mind sometimes we're going to have to interpret this as a limit, but we'll get to that. So plugging in z equals 1, we'll have a negative 1 for this term. Good. And then plugging in z equals 1 here, notice it's okay with this guy, we'll get natural log of 2. It's okay with this guy, we'll also get natural log of 2. But it's not okay with these two, we'll need to take a limit. So just to reiterate, we're okay here if we plug in z equals 1 and here. Keeping in mind that that's going to be multiplied by 1, because it's half 1 plus 1, and this is also going to be multiplied by 1. So adding those two things together, we'll have 1 times natural log of 1 plus 1, plus 1 times natural log of 1 plus 1, so that's going to be plus 2 times natural log of 2. And so just to reiterate, that's what we get from all of these green parts. Now let's see what we get from these parts that I'm underlining in red. So that's going to have to involve a limit, because if you notice, we have some sort of indeterminate form going on here. So I'm going to notice that this is going to be equal to, we need to add the limit as z tends towards 1. And it's important to notice it tends towards 1 from below because of how this antiderivative or this integral is constructed. Then we'll see that we're going to have z attached to the natural log of 1 minus z, and then negative half times 1 plus z squared to the rest. And that's because we have this minus sign here. So I'm going to go ahead and write that as a minus out in front of the whole thing. And then actually maybe minus 1/2 in front of the whole thing. So I'll just put it out there. And then we'll have z squared minus 2z plus 1 times natural log of 1 minus z. Good. Now, the next thing that I want to notice is I can factor that like z minus 1 quantity squared. And that's actually going to be really helpful because now I could apply L'Hopital's rule to this and then find that, in fact, the limit here will be equal to 0. So I'll let you guys check that, but suffice it to say this whole limit is equal to 0, which means we have gained the same value of the sum that we did in the previous method. And that's a good place to stop.